Okay, I'll get started. Last class, we talked about Monte Carlo methods, random number generation for random walks in one-dimensional and two dimensions. The famous example of a random walk is the Brownian motion. In this class, I wanted to talk about further random walks that we will solve with Monte Carlo method, we'll solve with random number generation. But these random walks are not through, say, one-dimensional space or two-dimensional, three-dimensional space, but rather through the states of the atoms and molecules of a gas, or the states through the atoms of molecules of a ferromagnet. So they too are random walks, like the Brownian motion was random walk, but they're through these different species of the spaces of states of a gas, states of a solid, that will allow us to explore and understand the properties of the gas and properties of the solid. And so we're going to do that in today's class. We're going to do some more of that in Wednesday's class. So it's kind of the theme for this week, I guess. I wanted to start because it's closely connected to what we do today. Something we did last week is closely connected to what we do today. With just a reminder of the coin tosses and the combinations and permutations that we saw in the coin tosses, because it is closely connected to understanding the properties of solids and gases in terms of the individual states of the atoms and molecules of the solids and gases. So I just made a table of something we talked about last Wednesday's class. Or we imagined tossing coins. Here I've imagined tossing 3 coins, and I've made a table of the possible combinations from tossing those coins and the possible what I would call outcomes from tossing those coins. And I'm going to introduce some new words for us, which are microstates, macrostates, and multiplicities. So for 3 coins, there are 2 cubed, so 8 possible combinations of the heads and tails of those 3 coins. So one of them is all heads upstairs here. One of them is all tails downstairs here. And then there's these combinations in the middle. These 3 combinations have 2 heads and 1 tails. And these 3 combinations have 2 tails and one head, if I've made the table properly. So the 8 possible combinations, so the 8 rows of the table, we're going to think of those as kind of the microstates of this system of 3 coins. So those are the microstates. And then these 4 possible outcomes. So the 4 possible outcomes are: you get no heads, you get 1 head, you get 2 heads, or you get 3 heads. Those 4 possible outcomes, 4 distinct outcomes, I'm going to think of those as being the macrostates of this three coin system. And one thing you'll notice is that there's only 1 microstate, 3 heads, for the 3-head macrostate. And there's only 1 microstate, 3 tails for the 3-tail macrostate. But for the 2 heads macrostate and the 2 tails macrostate, there's actually 3 microstates for each of those. So that makes, and I would call that the multiplicities of those macrostates. So the multiplicities for the macrostate of 3 heads or 3 tails is just 1. The multiplicities for the macrostates of 2 heads or 2 tails. That's three in both cases. And if you were to throw 3 coins, you're more likely to see outcomes with a large multiplicity of microstates. You're less likely to see something like 3 heads with a small multiplicity of microstates. I just made a little plot here to kind of picture this that might be useful later on. So horizontally are the different macrostates. There are 4 of them with 0, 1, 2, 3 heads. And vertically, I plotted the multiplicities. And here you see that the 3 tails and the 3 heads just have a multiplicity of 1, and the other 2 macrostates have multiplicities of 3. If we were to toss not 3 coins, but 100 coins, we can also think about the number of microstates and the number of macrostates and the multiplicities. And as you go to larger numbers of coin tosses, you see sort of interesting patterns emerge in the multiplicities of the numbers of microstates within a given macrostate. So for 100 coin tosses, so that's what I'm working out here, the number of combinations is 2 to the power 100. And 3, it's easy to imagine for 3. For 3 coin tosses, the number of combinations, 2 to the 3, 8. So now we got 100 coins, we got 2 to the power 100. That's a very, very big number. I put it in Google to figure out what it was. It's about 10 to the 30. So that's the number of combinations of different states, microstates, for just 100 coins. So it's a huge number. The number of macrostates is still a rather everyday number. You can have anything from 0 heads macrostate to 100 head macrostate. So there's actually 101 macrostates for this 10 to the 30, more than 10 to the 30 microstates. If you were to look at the distribution of the multiplicities, the number of microstates per macrostate, you'd see a very strong peak in the multiplicities for the macrostates around sort of half tails, half heads, around 50 heads, 50 tails. So the chance of throwing all heads, so no tails, is 1 out of this number of combinations, 1 out of 10 to the more than 10 to the 30. So that's now become, it's not like the three coin flips where, you know, getting 3 heads was kind of unlikely. Now it's almost impossible. Likewise, to get all tails, that would have a chance of getting 1 out of 1 times 10 to the 30. So again, it's almost impossible. To get 1 head or 1 tail and then 99 tails and 90 or 99 heads, that probability, that multiplicity is 100. So there would be 100 different microstates with 1 head in it and all the rest tails. And there'd be 100 different microstates with 1 tail of it and all the rest heads. So that's 100 out of 10, 10 to the 30. That's still incredibly unlikely. So if you were to plot the most multiplicities now of the 101 different microstates, in this case, you'd see they'd be strongly peaked around 50 heads and 50 tails. I think 50 heads, 50 tails is something like 1 times 10 to the 29 microstates. So that's almost 10% of the microstates are there. So it's got 10 to the 29 more microstates than no heads and no tails. Those those two microstates, and then it falls off pretty randomly, pretty rapidly around that number. So, you know, if you were to throw more coins, maybe you would throw Avogadro's numbers of coins, right? Then you can see the pattern. You'd have a extremely sharp peak for getting, you know, half of Avogadro's numbers of coins being tails and half of Avogadro's number of coins being heads. And the chance of getting all heads and all tails would be essentially nothing. So those two slides were just to introduce this language of microstates for the different combinations, the macrostates for the different outcomes, the multiplicities, and that some microstates have high multiplicities, and some macrostates are really unlikely to have very low multiplicities. The reason I did that is that those coin tosses kind of resemble situations in matter, in solids, in gases. The closest resemblance is perhaps for what we call paramagnetism. So many paramagnetic atoms are like little magnetic dipoles. And many paramagnetic atoms, they can just be orientated up or down. So each paramagnetic atom is just like a coin that could be head or tail, could be up or down. If you had a system that had 3 paramagnetic atoms that could either be up or down, then there would be 2 to the power 3, 8 microstates of that atomic system, that paramagnetic system. There would be 4 distinct macrostates with 4 distinct magnetizations. And there would be different multiplicities for the different states. So the states with 2 up atoms and 1 down atom, and the states with 1 up and 2 down, those would have multiplicities of 3. And then the other states with 3 up atoms or 3 down atoms, those would have multiplicities of 1. And so you can see there how what we worked out for coin tosses kind of could resemble a paramagnet. A paramagnet would have more atoms though, but you know, so this case of 100 coin tosses better, you know, represents or kind of simulates a paramagnetic material. If you've got 100 atoms in that material, then you're going to find that you've got 10 to the 30 microstates. You've got 101 macrostates with different magnetizations, but by far and away with the highest multiplicities, the macrostates with, you know, half of your atoms up and half of your atoms down, half of your magnetic dipoles up, half magnetic dipoles down, are going to be the most common state. Okay, so that's kind of the analogy between macroscopic systems like gases and solids with that simple system of the of coin tosses, in large numbers of coin tosses. And we're going to draw on that analogy to try and understand some problems in statistical mechanics. So in classical mechanics and in quantum mechanics, we're normally dealing with, say, a single state, single object. It's statistical mechanics. It's kind of the world of dealing with the using statistical methods and probabilistic methods to consider states that are ensembles of many atoms or molecules, And the sort of problems that you might want to solve for those ensembles of many atoms and molecules might be properties of the gas, properties of the solid. For example, like the magnetization of the magnet, or maybe like the pressure or energy of the gas. Those are the type of problems that we're going to solve in statistical mechanics. So you can probably now see that the Monte Carlo methods can be applied to the statistical problems of these sort of ensembles of many atoms or molecules. It's really because in those ensembles, there's a lot of processes that are either truly random or seemingly random. And so we can model them with Monte Carlo simulations. The two cases that we're going to do, one in today's class and one in Wednesday's class. Today's class, we're going to look at the internal energy of a gas, kind of a quantum gas. So we're going to calculate the internal energy based on the temperature of the gas with a Monte Carlo method. And then the one that we'll do on Wednesday is we're going to think about a solid ferromagnet, say iron or cobalt or nickel, and we're going to calculate the magnetization of the iron using Monte Carlo methods. So these are two sort of relatively straightforward applications of Monte Carlo methods to macroscopic systems of solids or gases. The specific method we're going to use is I put it on the slide. It's called this Markov Chain Monte Carlo. So that means that it's what it is kind of a random walk, not through one-dimensional space, two-dimensional space, but through these states, the microstates of the gas, or the microstates of the ferromagnet. So we're going to walk through those states. And as we walk through those states, kind of we'll calculate the next step in the random walk based on the prior step in the random walk, prior location of the random walk, kind of like we did in, looking at Brownian motion, or one-dimensional, two-dimensional versions of Brownian motion. We would calculate the next step based on where we were in the prior step. Okay, so this is a specific problem for today's class. We're going to imagine that maybe we got this big reservoir of some material or medium, maybe a tank of water, which has some huge internal energy because big reservoir, and it has some fixed temperature. And we're going to place inside that some sample of gas. And of course, it's going to come to equilibrium with the small sample of gas will come to equilibrium with the massive reservoir. So they'll both be at the same temperature. And we're going to work out the internal energy, the total internal energy of that gas sample that's shared between the atoms or molecules of the gas. So that's the problem we're going to work on. And we're going to do it by this Monte Carlo method. So here here's just defined a few terms, So reservoir, this is the big vessel. The sample, this is the small sample. T is the temperature. Here's the energy of the reservoir. And we want to calculate the energy E of the sample, the internal energy E of the atoms and molecules of the sample. Here I'm just trying to say that, as if you change the state, the microstate of the sample, so supposing you increase its energy or decrease its energy a little bit by changing the state of one of the atoms in the sample, then there's got to be a corresponding change in the energy that's stored in the reservoir. But we're going to think of the reservoir as huge, so its energy change is negligible. and we only yet really think about the energy change of the sample that's in the reservoir. Okay, so we need a procedure for calculating observables of a macroscopic system like the gas from the knowledge of the microscopic states of the gas. In this case, we're calculating an observable that's the internal energy. And again, we're going to be calculating it for this macroscopic sample of gas based on our understanding of the microscopic states of the atoms and molecules in the gas. So on this slide, I got a couple of equations. I will label this one number 1, this one number 2. These are going to be important to us. I want to define these equations, but I just want to sort of talk about them a little bit so that they sort of make sense to us physically. I mean, I'm not proving these equations, but I'm going to try and at least motivate these equations. So this equation number 1 is the equation for some physical quantity. So we're thinking about the internal energy, that it could be the magnetization of a solid. It's an equation for the value of that physical quantity of this macroscopic system in terms of the value of that quantity, so the internal energy of each microstate, and the probability of having any particular state. And so xi subscript I, that's the value of, say, the internal energy for a particular microstate. And pi is the probability of having that particular microstate. And then we're just adding this up for all the microstates of the macrostate. So I would just think of this as kind of like averaging. Just think of the 3 coins. You know, you've got these different microstates, and each one of them has some internal energy, say, and you're going to just add up you're basically averaging the internal energies of all those 8 different microstates. You're multiplying each microstate's energy by its probability and then just adding it up to calculate the average. So that probably makes some sense. The probabilities in here of occupying a particular microstate of a particular energy. So here's the energy of the microstate. We're going to try and calculate the energy of the system, but here's the energy of a particular microstate. Are given by this formula down here. This is called Boltzmann's formula. So this formula tells us a probability, and it contains these 2 pieces, one in the numerator and one in the denominator here. In the numerator, we got this exponential, which is e to the minus beta times the energy of the microstate. Beta is nothing other than 1 over kT. So 1 over the Boltzmann constant times the temperature. So this is e to the minus energy of the microstate divided by kT. And then in the numerator, in the denominator down here, we got a factor. It's normally given the symbol z. It's called this partition function, which is really just the sum of the Boltzmann's factors for every microstate of your macroscopic ensemble. So you just add them all up to get this this partition function z here. And so this is how we're gonna calculate the probabilities. Let me say on the next slide a few features of that equation for the probabilities to motivate that equation for the probabilities makes sense. So firstly, I'm going to focus on this equation for the partition function of probabilities. if you look at that negative exponent, it's telling you that the ground state is the state that's firstly going to have the highest probability. And that higher excited states with higher energies will have lesser probability. So it's this probability factor is going to be weighting the internal energies in our case. And the ground state energy will get the highest weighting, and excited state energies will get lesser weighting. It also tells you that maybe a good reference point is KT. So if there are states where the energies are, say, less than KT, well, they don't get weighted as much as the ground state, but they get weighted pretty similarly to the ground state because it's e to the minus a number that's less than 1. So they're going to get a decent weighting in this, this averaging procedure. If you've got states that have energies, greater than KT, especially much greater than KT, then that's the that Boltzmann factor is e to the minus a big number. So those are going to get very little weighting. We're going to get a very small weighting in this calculation of the average. So one thing that the Boltzmann formula is doing is weighting different states based on their energy and based on that comparison to KT. Another thing that happens is that supposing you were to adjust the temperature, you would change the temperature. So if you increase the temperature, you're going to weight more and more those higher energy states. They become more important. If you decrease the temperature, you'll weight less and less those higher energy states. And so temperature will kind of control through that KT the relative importance of the high energy and the lower energy states. And so that's how the probability function, that's how the Boltzmann formula for the probability of these different microstates is being calculated. And I certainly haven't proved that equation, but hopefully it makes some sense. The division of the Boltzmann factor, e to the minus e over kt, by the partition function, is just to normalize things right. You're dividing the Boltzmann factors by the sum of the Boltzmann factors so that the individual Boltzmann factors are truly probabilities. And when we calculate that average, we're just taking the probability for each microstate. So that's all very nice, that equation. We could calculate the the internal energy of a gas by following that pair of equations. But there is a big problem with it. So if you had any reasonable number of gas atoms, supposing even if you had 100 gas atoms, like 100 coins, that's a sum over the microstates. And so that would be a sum over, for 100 coins, it was more than 10 to the 30 different microstates. That would be computationally extremely challenging. So whilst the equation is kind of simple, and the equation sort of relatively easy to conceptually understand, carrying out the calculation would be very, very difficult. And that's where the Monte Carlo method comes in. So the Monte Carlo method comes in that instead of carrying out the entire sum over all the microstates, we're going to take this random walk through the microstates to kind of gravitate to the average value of, say, the internal energy in this particular case. So that's what this Markov Chain Monte Carlo method does. And it's a fairly straightforward series of steps. So let me just I'll go through the steps, and then I'll kind of try and, again, sort of motivate the steps, not prove the steps, but justify the steps. So there's a list of 4 steps here in which I'm going to try and I'm going to calculate the energy in our example, internal energy, or it could be some other observable of a particular microstate. And then we're going to take a random walk in these microstates until we end up with a stable value for the energy of the microstate, which we'll interpret as the average value for the internal energy of that system of gas. So the first thing you do is just pick some convenient initial microstate. So imagine right now that we've got 100 atoms of gas in our sample. We're just going to pick some initial condition. Maybe we pick them all to be in the ground state. That would be a simple condition. And then at random, in step 2, what you're going to do is pick one of the atoms in the gas, so one out of these 100 atoms in the gas, and we're going to change its state. We're going to raise its state, or if it's excited, we could also lower its state by kind of one unit. So we're going to change its state, and then we're going to recalculate the energy for this new. We changed the microstate, so we've changed the old microstate into a new microstate. We can recalculate the energy for the new microstate, and then we'll accept or decline that new microstate based on this kind of rule here that's in step 3. So this looks like the most complicated step. What it's saying is that we're going to accept or decline that change from the old microstate to the new microstate based on a couple of rules. So if the energy has gone down, the energy has decreased, then we will accept it. We'll always accept it, unless the only reason you wouldn't accept it is if you're trying to decrease the energy below the ground state. Then you couldn't accept it. So that's the rule for decreasing the energy. If you increase the energy, right, then what we're going to do is we're going to accept it with a probability that's based on that Boltzmann factor in the argument, the difference between the old energy and the new energy. So that's this little guy over here on the far right. If I go down in energy, I'm going to always accept it, probability of 1, unless I'm at the ground state. If I'm going to go up in energy for the microstate, I'm going to accept it with some probability, something that's less than 1, where the argument in this Boltzmann factor is now the difference in the energies between the old and the new microstate. So this will give us a probability that's less than 1. If I do accept it, whether I went up or went down, then in item 4, I can recalculate say the internal energy or the particular observable for the microstate. And then I'm just going to repeat these steps 1, 2, 3, 4 many times. I might repeat, I think I'm repeating them like 10,000 or 100,000 times. And what happens when you keep repeating them, right? If supposing you started with everything in the ground state, but the bath is at some reservoir is at some temperature, right? Well, your sample is too cold, basically. And so as you start changing the microstates, it's going to warm up. You're going to move your atoms and molecules into excited states. So there's going to be this kind of burn-in period where the state is over the random walk is changing. But then you get to this period where it kind of equilibrates. You're going up and down in energy, but you're basically staying in thermal equilibrium with the reservoir. And once you spot you're in the equilibrium after the burn-in, then you can interpret the energy of the state, of the microstate, with that being, at least statistically, the average energy of the sample. So that's the procedure. This is just a slide to kind of argue a little bit why this procedure works. So the idea of the random walk is basically that we can't do this calculation for all the microstates. We're going to have to use the random walk to, in this fashion, work our way to an average state. And what helps us is that the multiplicity of average states that have the right temperature is very high. Just like, 50-50 heads and tails is a very high multiplicity. All heads, all tails is a very low multiplicity. So that helps us. As I say, if we go up in energy, we penalize that transition based on this sort of Boltzmann cost of the probability of going to higher energies. So in that way, we're using the Boltzmann distribution in tailoring our random walk. So that's where the Boltzmann distribution enters. The fact that we accept downward steps unless we bump into beyond the ground state is also consistent with the Boltzmann factor, right? There's no energy inhibition or net energy cost associated with going down in energy. And so in items 2 and 3 on this list, we really built in the Boltzmann distribution through these penalties for accepting or declining that particular step from the prior microstate to the next microstate. And as I say, this is how we're going to walk from some very unlikely state with everything it's like we start with everything heads if we start in the ground state. We're going to walk our way to the high multiplicity state, a kind of average state. Last couple of slides, just a couple of specifics about the allowed states of this quantum gas that I'm going to use in this. So we need to know if I increase the energy by kind of 1 unit to the next excited state, or I decrease it by 1 unit, how much change of energy that is that in terms of the nature of the gas, the mass of the gas atoms, say the size of the box that the gas is, and so on and so forth. So I'm just going to use for this exercise, right, well, I'm going to imagine I've got quantum mechanical particles in a one-dimensional box, and I've got the allowed energies for a quantum mechanical particle in a one-dimensional box. So here are my wave functions of my particles that fit in the box, or at least the first few of them, and which you know well. And here's the energy in terms of the principal quantum number. The size of the box is L, and the mass of the particle is M, and Planck's constant. So these are the energy levels that I'm allowed. So maybe, as I say, I'm going to start my code with every atom in the ground state, n equals 1, and then I'm going to start at random picking atoms and changing its energy. So they'll start increasing their energies to begin with. And so I'll be going from n equals 1 to n equals 2, and then maybe I'll go from n equals 2 to n equals 3. But later on, I might be also, once I get out of the ground state, I can also lower the energies. And so I might go from n equals 2 to back to n equals 1. So the actual energies that I need are these energies here. So there's the energy change when I go from a state n to n plus 1, and that's this little formula here. So I just took, the formulas for En and En plus 1 and the difference between them. And then the other possibility is I lower the energy by one principal quantum number, and that's this equation here. Again, it's just the difference between the energies of En and En minus 1. And these two equations are what I'm going to be using in my code. So when I've got my system of atoms and I say, well, I'm going to, you know, I'm going to run it, pick this atom, and I'll either increase its energy or decrease its energy. When I do that, it's by these amounts.